This is lecture number 23. In this lecture, we are going to talk about stability and performance comparison using MATLAB simulation. And this is, we are going to consider here variable frequency control as well as fixed frequency control. And I want to also demonstrate some MATLAB simulation of different control technique, current mode control technique and their comparison. So, the main concept which I covered today class is a MATLAB simulation of ripple based control, as well as we have already simulated for fixed frequency control. Then we want to compare performance using fixed and variable frequency control, particularly we will talk about current mode control. So, current mode control context. Then we want to talk about stability comparison like a fixed and variable frequency current mode control method, and then steady state ripple parameter under current mode control. We want to do a comparative study. Okay, and so that means our objective here we are considering under continuous conduction mode, and we are talking about like a synchronous configuration, that means always under continuous conduction mode, and we are going to talk about peak current mode control, valley current mode control under fixed frequency. Also we are going to talk about constant on time, constant off time as well as hysteresis control, all are in under current mode control, and then we want to see the comparison. So, I want to start with the basic modulator. This is a building block. Okay. So, if you want to implement a current mode control logic, the first thing that we require an analog comparator. So, this is my analog comparator. So, in this analog comparator, that means this is our analog comparator, and then this analog comparator is used to compare between the reference current and the inductor current. Okay. So, here this inductor current we are showing, it is a sense inductor current. So, first we want to see MATLAB implementation of ripple based current mode control. So, in this context we will talk about peak current mode control, then valley current mode control, then constant on time. So, which is analogous to, so this is analogous because both use valley current control. Okay. So, both control valley current, and the constant of time, this is analogous. Okay. So, this is analogous because it can control the peak current control. Is a peak current control. And finally, hysteresis control. Hysteresis control can be configured in peak version, that means I will come to that point, and it can be also configured to valley. So, depending upon, so for example, if you are talking about it require a hysteresis band. Suppose we are talking about a hysteresis band like this, and now we want to keep our inductor current within this band. Okay. So, within this band, this is our peak reference and this is our valley reference, and this is our actual inductor current. Okay. Now, if we set I peak to be equal to I reference, and then I valley is simply I ref minus delta IH. That means, we are going to directly control the peak current, and the hysteresis band, which is nothing but this band, this is used to control the ripple of the current, as well as this is used to control the switching frequency. Okay. So, this is here we are setting like a peak configuration, peak current mode configuration. Now, if we want to do valley current mode, like suppose if you want to do valley current mode configuration, then what we will do? We will simply set IV to be I ref and IP to be I ref plus delta IH. Okay, just add the hysteresis band. And if you want to implement in average current mode control, then you simply set I peak to be I ref plus delta IH by 2 and I value to be I ref minus delta IH by 2. So, this will implement average current mode control. That means, if you use a hysteretic controller, then you can very fast average current mode control you can implement simply by using this configuration. But we will see this configuration suffer from variable frequency. Okay. So, sometime it is not possible, and in fact, you need to sense the complete current. So, we will discuss some of this aspect. So, in fixed frequency peak current mode control, we are talking about this modulator. Now, if we draw the inductor current waveform, let us say, so in peak current mode control, we are reference current act as the peak reference current, okay, and the inductor current will simply follow. That means, when it hit the upper limit, it turns off, and then it turns it turns off. So, it is under trailing edge modulation, that means trailing edge modulation, and we have discussed multiple times. So, it is trailing edge PWM, where the switch turns on at the rising edge of the clock. At the rising edge of the clock, the switch turns on, here the switch turns on, okay, and the switch turns off whenever the comparator, that means inductor current, hit the peak current limit, okay. And the modulator structure will look like this in this peak current mode control. So, if we want to implement MATLAB model, so we have already this converter. So, this is our converter model, and we have already implemented, and here we are using resistive load, and we can make a load transient by using a constant current load, external load, and this is our input voltage. Here we are talking about the ideal voltage source, and we can add a input supply transient here. Then we can also create a reference transient by applying a step transient here, and this is a reference voltage. What is inside this block? So, this block inside, this is our error voltage, right, because this is our reference voltage, this is the output voltage, and this is the controller, okay, and this controller we are actually programming in the .m file. So, we are not separately putting a controller. So, if you click on that, it will you will find the numerator S, which is here. You will find, if you go, it is the numerator under controller, that will see shown. And if you go to denominator S, then you will see denominator controller, okay. So, if you go back to a MATLAB file, I will just show you the peak current mode control. This is what I am showing here. So, if you go inside, then this is the model, numerator control and denominator of the controller, those we are programming from the MATLAB file, okay. So, we are not separately controlling. Now, you can see there is a separate sawtooth waveform, that means this is our ramp compensation or some compensating ramp. We may or may not need this, because in general, if the duty ratio is much lower than 50%, we may not need this one, we may not need. But as we go for higher duty ratio or even for higher gain also, you may need to consider ramp in order to stabilize the current loop, okay. So, this is the error voltage, this is the inductor current. If the ramp is not there, as if this is the inductor current is directly compared here, okay. And this block, this particular block, if you see this including this clock, it is our trailing edge PWM, block, okay. Now, if you go for fixed frequency valley current mode control, now this architecture, our reference current is our valley current, and inductor current should be above that reference current, and this is exactly shown here. So, here this is our valley current reference, this is our valley current reference, okay, and inductor current here, it is leading edge modulation, leading edge PWM. So, here at the beginning of the rising edge of the switching clock, the switch turns off fast, and then current continue to fall. Then when the current hit the reference current, which is the valley current, then the switch turns on, and switch will remain on until the next arrival of the next clock edge, okay. So, then again the switch will turn off. So, this is a process under valley current mode control. And if you want to, and this is a switching frequency is used as a trigger pulse here in the generic block, okay. So, if you want to implement the MATLAB model, then again this block is known, everything is common, we are not going to change. What is inside the valley current mode? So, here again this transfer function is the controller transfer function. So, this is our controller transfer function, and again this is our error voltage. So, this particular point is our error voltage, which compare reference voltage minus the output voltage, then transfer function, then this is our this is our valley current, that means this is our I ref that we have discussed. Okay. Now, in this case again you can use a RAM compensation, okay, a RAM compensation, and you will find here our ramp is subtracted. Basically, we are talking about a positive ramp, because why? Here we are talking about valley current mode control. So, if you look at this valley current reference, the inductor current is actually like this, and then it goes up like this. So, here we have to add compensating ramp, and add means what? The falling slope. So, if you want to add with the falling slope, that means your falling slope is minus M2. That means our ramp should also be falling slope, right? Then only you can add. That means we want to achieve minus M2 dash, which is nothing but minus M2 minus MC, where minus MC is the slope of this. That means if I take a ramp, this ramp, and if this ramp slope is MC, then if I want to subtract here, then I need to subtract here. So, this point should be subtraction, okay. And this is added in case of peak current mode control, because there we are talking about the rising slope and we have to add ramp. So, both will be added so that actual slope, effective slope will be higher. So, here we are trying to increase the effective falling slope. So, we need to subtract the ramp, where we are talking about the ramp to be a positive slope ramp, okay. If you take a negative slope ramp, then it should be added, okay. So, now we are talking about constant off time like peak current mode control. So, this is analogous to our conventional peak current mode control, but here the earlier conventional peak current mode control, our time period is constant, here off time is constant, and you can see this off time is constant. So, here how it works? Initially if the switch turns on, then when it hit the peak current limit, then switch turns off, okay. So, the switch turns off. Then when switch, how long switch will remain turn off? The duration is decided by the monoshot timer. It is decided by the monoshot timer, okay. So, this comes from the monoshot timer. This is our off time, okay. It comes from monoshot timer. When the timer completes its counting, then switch turns on, okay. And then when switch turns on, then current will continue to rise, and again it hit. So, that is the logic. So, what is the trigger pulse here? So, here the trigger pulse is that when the counter actually complete the counting, that means this is the time when the counter will stop finish counting and it create a trigger pulse. So, that means this will come from, you can say, when the counter will start. So, this is our trigger pulse will come from there. So, how to implement this constant of time? Again this block is common, so there is no change. Now, we have only changed this block, okay, and we need a current feedback. So, all control technique we are talking about a current based control. So, the current feedback is essential, that means this is my current feedback, okay. So, this is essential, and since we want to regulate the output voltage, reference voltage and the output voltage should be there. If we go inside this block, because we want to see what is inside this block, then again the controller is common. This is our GC controller, and this you can think of a reference current, okay, and here this is our error voltage, and we will see soon that such technique do not require any ramp compensation, because they are inherently stable. The current loop is inherently stable for the entire duty ratio range. That means Unlike in peak current mode control that we are familiar with, if current loop become unstable when the duty ratio goes beyond 0.5, in fact it can be unstable even lower than 0.5 if the controller gain is high, then we need to add RAM. In case of valley current mode control, if the duty ratio is lower than 0.5, the current loop is unstable and we need to add either negative slope RAM or subtract a positive slope RAM, that we have discussed. But in this case we do not need a RAM. So then this current and reference they are compared, then what is the next task? So the next is, this is our comparator output, like this output, comparator output. This output now is trigger circuit is used, that means we are rising, this is a rising edge, this is a rising edge, okay. So this trigger pulse is used as the input to the monoshot timer. So this is the timer where we fix the off time, this is the monoshot timer, okay. So this is a monoshot timer, In fact, why don't we go to the MATLAB directly? So if you go to MATLAB, okay, now if you open this peak current mode constant on off time, you will find that this is the block that we have discussed, the feedback block, okay. So just hold on, okay. Now this is our feedback controller. If you go inside, this is what we have just discussed now, okay. So this is our monoshot timer where we are setting the constant off time, okay. Now what is this? This block is used as a minimum on time, because we have discussed earlier, if we do not incorporate this minimum on time, then the whole system can collapse, and it is nothing but you need to detect an edge, and this is a delay block, and then it is compared. So this aspect we have discussed in the previous lecture when we discussed detail about the constant off time. So we are not going to spend time on that. So that means this part is clear. Next we are talking about constant on time valley current mode control. So this is similar to our fixed frequency valley current mode control. The only difference here, we are fixing this on time rather than time period in the earlier case, okay. So on time is fixed, and here you can see it initially the switch turns off and the inductor current start falling, right, and whenever the inductor current actually hit the reference current, then the monoshot timer is activated. So this is where it activates the monoshot timer, So the monoshot timer will now, this duration it is on, and here it will finish the counting and then switch will turn off, okay. And again in this technique also, if you want to implement in MATLAB, so this part is common. So this is the constant on time controller that we are talking about. So we want to see what is inside this block, okay. So if you go inside in the valley current mode control, you will find again this is our error voltage, okay. So this is our error voltage, this is our controller, this is our reference current, and this is the inductor current, okay. So here this is the block which is our modulator, like constant on time modulator, and here we are setting the on time, and using a monoshot timer, okay, and then here this block is used to set the minimum off time, okay. So this is, now if you go inside this MATLAB block, okay, so this is the monoshot timer, I mean in a constant off time, where if you go inside, this is what I have shown, and if you go inside, then you will find this is where we are setting the minimum off time, okay. So this is the MATLAB realization, minimum off time, this is a delay block, okay. So all these logics are discussed under the context of constant on time, okay. So that means we are familiar with this, all this control logic. Now let us go to our presentation. Now current hysteresis control. So we have discussed under the hysteresis control that actual current hysteresis control can be realized by using the sense inductor current, and we can use a hysteretic comparator, okay, and those things. But now for sake of simplicity in the realization, here we are realizing a current hysteresis control by using a 2 comparator structure, but this is for simulation. In actual circuit, 1 comparator with hysteresis should be sufficient. Okay. So, here we are limiting the current in between the maximum and the minimum value, and this is our hysteresis band. Within the band we are trying to limit the inductor current, and we will see in fact that if you set the current reference just using constant current value, then you can find out, because this is the inductor ripple, the ripple inductor current will be equal to delta IH. That means both are equal if you set, if you fix references are set. But if the loop is closed, that means if one of the reference is coming from the outer loop and then you add or subtract the hysteresis band, in that case you will find the actual hysteresis band and the actual inductor current, they will be different. In fact, the current ripple will be smaller than, so I will say that the current ripple will be smaller than delta IH if outer loop is closed. Okay. So, current hysteresis band can be realized. So, this is where we are just changing our controller, all other things are same, and here this is our current reference. So, here this is our reference current and this is our error voltage, this is our controller, and this is nothing but delta IH by 2, and this is also delta IH by 2. So, this is our peak current is a max value, the upper limit, and this is the I mean. If we go back in order to make it consistent, yes. So, this is the I max that we are talking about, I mean. So, it is here, and then we are using comparator, like these 2 comparators are used and the RS flip flop. Okay. So, by that we can implement. Now, we want to first see the current loop stability analysis. Okay. So, this is the current waveform. You can think of this is the peak current architecture. This technique you can use either using fixed frequency or constant off time, or even you can take hysteresis. So, the first thing we want to obtain the sample value of the inductor current or the final value of the inductor current. Let us say this is our n TS cycle and this is our n plus 1 TS cycle. That means, at the end of the cycle, what is the value, which is I n plus 1, and initial value is I n during the cycle. So, I want to write the final value of the I n of the final value of the inductor current in terms of the initial value of the inductor current. Then we want to justify stability. So, first thing, from this equation you can write I ref, which this is I ref, minus M2 is the falling slope and this is the off time, where what is I n? I n will be equal to I ref minus T on n, this is our I n. Okay. So, if you continue under fixed frequency control, our T on is nothing but d into t and T on is 1 minus d into t. Then if you write earlier equation I n plus 1, we wrote I ref minus M2 into T off. So, you replace T off here with this 1 minus dt. Then I want to get this dt. So, what was I n equation? It was I ref minus M1 into T on. So, T on is nothing but dt. So, from this equation I want to find d from here. So, okay. So, if you want to find dt, basically you have to find out dt. So, I will say you find out dt. Then we substitute this one into this equation, and then what we will get here? Now, we are writing the complete current equation. Here this is the final current, and if you write the whole expression, it is a function of the initial current, reference current and the slope. Now we are talking about the part of current dynamics. In order to obtain this part of current dynamics, that means here we are replacing In equal to capital In plus In part of, then we can write Iref to be capital Iref plus Iref part of. So these two, and we are not considering perturbation in the slope. That means there are two assumptions: the perturbation and the slopes are neglected, and the nonlinear product which will come out from here of the perturbation, those are also neglected. So that means the linear equation, part of equation is like this. Now you will find two things here. The one thing, okay, so here there are two things you can write. One is called zero input stability. What is that? Zero input stability, that means when there is perturbation in the external input is set to 0. That means we are using a fixed current reference. The current reference is not perturbed, and we are not exciting, like there is no external excitation in the current reference. So it is a fixed current reference. Then this equation will simply become this equation will become, that means we are talking about In plus 1 perturbation is equal to minus M2 by M1 into In. That means this we are going to justify stability for the inner current loop, and that is a zero input stability. If we can show that magnitude of M1 by M2 less than unity, then this will be stable. This can be shown it is stable if this quantity magnitude is smaller than 1. The other term that we are familiar with is a zero state stability. Zero state stability. Here we are talking about the stability, that means here we are setting the initial perturbation in the inductor current is set to 0, and we are trying to find the current perturbation as a function of that 1 by M2 by M1, this perturbation into Iref. So this will show that the current loop stability when we are exciting from the external current reference, but setting the initial current 0, but this will be only valid only for that particular cycle, because the next cycle onward your current initial value will also give, because this perturbation will keep on accumulating, and either if it is stable it will slowly decay out and the current will come to steady state, or it will go somewhere else, and that we have discussed in the previous I think lecture number 19, that it can lead to subharmonic oscillation. Okay. That means for constant current difference, where we call it about zero input stability, for inner loop, that actually gives us the inner loop stability, the magnitude of M2 by M1 must be smaller than 1, and for if you take a buck even boost or even buck boost, and if you take M1 slope for the buck and M2 slope for the buck as well as boost, and if you substitute this equation, that means this magnitude, then it can be shown that inner loop will be stable that when the duty ratio is less than 0.5. That means under peak current mode control, the inner loop stability, but this is less than 0.5 is it is not the sufficient condition, it is the necessary condition. The sufficient, if you close the outer loop, it may so happen the actual current loop stability, the whole overall stability may be at a lower duty ratio. That means it can be even less than 0.45 or so or less, depending upon how are you setting the outer loop voltage controller gain. Okay, but only for inner loop stability the requirement is that it has to be less than 0.5. Okay. Now for boost converter also you can substitute M2 M1, and then you can get the same result. You will get the current loop stability for current loop stability under peak current mode control. Okay. Now, the same thing if we go for constant off time control. Okay. So, constant off time control, we know the on time is coming from the outer loop, because on time is decided by when the inductor current hit the peak current difference, but the off time for constant off time control is fixed. Now, we can refer to the same inductor current waveform which we did earlier. That means, if we go back, the same current waveform you can, if you take this current waveform, now In plus 1 In everything is known, then we are writing this equation. Okay. So, here In plus 1 I ref M2 minus Tc. Now, since this quantity is constant, that means, and this is an external current difference. So, the final current is simply a constant quantity and it is a function of the reference current only. So, it is independent of, that means, if you take the perturbation, In plus 1 is only a function of I ref and this constant current difference, it is 0. So, In plus 1 0, this indicates the current loop is inherently stable irrespective of the duty ratio. That means, if you change the duty ratio very widely, the current loop will never become unstable. That is the beauty of this constant off time control. So, you do not need a compensating ramp. Now, in fixed frequency valley current mode control, then we can show that the same method can be applied to derive the current In plus 1, where here the In plus 1 we are talking about this current and this is my In. And if you write the whole equation, again if you perturb, if you write one by one what are the equation In plus 1, then what is the expression of In, from there you are finding 1 minus dt, and then if you substitute, this is the overall equation. That means, this is my In plus 1. Again there are two terms, one is the initial current, another reference current, and if you ignore the slope perturbation, the part of current dynamics. So, it can be shown that for inner loop stability you need M1 by M2, that magnitude should be smaller than 1, and this will give rise to the condition that D should be greater than 0.5. That means, for valley current mode control, the current loop will be stable if the duty ratio is greater than 0.5 and it is unstable if the duty ratio is less than 0.5, and you can stabilize this current loop by using a compensating ramp. Okay. So, constant on time, if you consider the constant on time control, it can be shown that what is In plus 1 here, In plus 1 should be equal to what? It is, so this is In plus 1, it is nothing but I ref this value plus M1 T1. Since T1 is constant, I ref is the external source. So, if you take the In plus 1 perturbation, it is simply function of the reference current perturbation, okay, and this is written here, and that means the current loop stability is independent of duty ratio. That means, it will be stable for a wide range of load current, okay, and that is why we discuss in lecture number 19 that for low duty ratio voltage regulator module like low voltage high current application, now the constant on time control is kind of as a very popular choice over fixed frequency current mode control. So, the performance comparison, if you want to do MATLAB simulation of this audio susceptibility, transient response for low duty ratio operation, high duty ratio operation, current loop stability. So, we need to check all this. Let us go to the MATLAB simulation. Okay. So, what are we going to do? We want to first use a say we do not want to use any ramp compensation. So, here in this code we are identifying the parameter. In fact, this is not required, all these things are not required. So, this only requirement is this, okay, and you have to set the input voltage, load current and so on, and this is my modulator voltage. So, if you use a ramp compensation, then you have to set what is the maximum value, and we are simply taking a PI controller common for all technique, and here we are applying a reference voltage transient of 0.1 volt, and we want to compare the performance using different controller. Okay. Now, we are going to this simulation and load current is 1 ohm, So, let us first set, and we are using the blue color waveform trace, and initially we are going for peak current mode control. So, let us say we have different controller here, we have stored here. So, let us say if we run the peak current mode control, and I have shown all the diagram here. So, first I am drawing the peak current mode control. Okay. So, this is, it shows, okay, just hold on. So, we want to change the initial condition to 1, okay. So, we want to rerun. So, what I am showing here, this is my using peak current mode control, and it is my reference voltage transient. That means, I am setting some fixed gain and just comparing how does the controller respond for different control techniques. So, it is a reference voltage transient using peak current mode control. Now, of course, this technique cannot be, because the duty ratio is here, input is 12 volt and the output is 1 volt. So, you should not use valley current mode control because it is completely unstable. Okay. And if you want to use valley current mode control, then you have to use a very high ramp compensation. So, let us say if you use a valley current mode control with a voltage of maybe 50, because it is a very low duty ratio operation. In fact, we should not use in this technique. For high duty ratio, we will go for that. Now, as we said in lecture number 19, for low duty ratio operation, since you have a very small on time, you will get hardly any time to continue the comparator operation, and all this we cannot finish within that very small amount of on time when you are talking about a high switching frequency. So, then we talk about the valley current mode control, but valley current mode control for low duty ratio is unstable. So, that we have discussed, we will go for constant on time. So, if you do constant on time, that means this is my constant on time. So, I want to compare the performance using constant on time, which is the case here, and now I am using another color, which is a red color. Okay, and let us run it and see what happens. So, here we are comparing with constant on time, and I have already shown all this architecture. Okay. Okay, so this is the performance under constant on time control. Okay, and if you see the inductor current reference for the same controller gain, if we use one is our peak current mode control, which is the blue one, and the red one is the constant on time control. Okay, and you will see in this particular case the constant on time control seems to be better because it has almost no overshoot. Okay, for this controller. So, that means if we want to obtain the small signal model for the same constant on time control and the peak current mode control, they should be different, because for the same controller their response are different. So, the constant on time seems to be over damped response, there is no overshoot here. Okay, but whereas the peak current mode control is giving a high overshoot because it is much higher, it is roughly around 10%, 10 to 15% overshoot is we can get it from here. Okay. We also want to compare the hysteresis control. Okay. So, now we are going for hysteresis control. So, let us compare the hysteresis control, and we will use a different color. So, for hysteresis we will use, let us say, black color, and let us run it. So, for the same configuration we are now running hysteresis control, all these are same. Now, in hysteresis control, you see this is something similar to our peak current mode control. Okay, and if you go to this block, you will find hysteresis control, the current is within a band, but though we have said 4 ampere band, but it is not actually 4 ampere, it is less than that. Okay, because if you go back to the actual MATLAB file, we said the current hysteresis band to be 4 ampere, and I have discussed if you close the outer loop, the actual current ripple will not be equal to the hysteresis ripple, and we will whenever we will discuss at the end, I will refer some paper and show it. It is actually when you fix only current reference, they are true, otherwise the actual current ripple will be less, because the black color you see the current ripple is, it is smaller than 4, because -1 to 3 is the 4 ampere band, but it is smaller than this. Okay. So, you have compared. The last one which is left is that we need to check now peak 1. So, peak 1, because we need to evaluate their compare how can we compare their performance. So, the fourth one is this the peak, that means the constant off time control. Okay. But valley current we cannot use because the low duty ratio it will be unstable. Okay. And you will see in this case it has much higher overshoot, unacceptably high overshoot using constant off time controls. Now coming back to that, means we can check the audio susceptibility. So if you want to check the audio susceptibility, so we have checked this point, the low duty ratio operation transient response we have checked. Now we are going to check for high duty ratio operation. Let us go for high duty ratio operation. So in high duty ratio operation, our objective, let us say we want to operate around 8 volt input, like means 12 volt is the output and 8 volt is the input. Okay. So 8 volt we are setting reference voltage to be 8 volt. Same controller we want to compare 8 volt. Okay. Now as we discuss that we should not use peak current mode control here, because peak current mode control our duty ratio is, it is 8 volt by 12 volt. That means if I go back, I am talking about this scenario, we are initially here we took 1 by 12, that means that is our equivalent duty ratio, which is equal to 0.083. It is a low duty ratio operation. Now we are talking about 8 volt to 12 volt. Okay. And which if you write in terms of equivalent duty ratio, it will be how much? So 0.75 duty ratio, that means it is 4 by that means it is 2 by 3, sorry, it is 2 by 3, not 0.75, I am sorry, it should be 0.67. It is, that means it is equal to 2 by 3, it is nothing but 0.67. That means it is higher than 0.5. Now let us go to the MATLAB. So here we should first use valley current mode control. So this is our valley current mode control. Here we are talking about valley current mode control. Okay. And we want to first simulate using blue color. So blue color. So here we are making a reference transient response, and you see it is stable, okay, under valley current mode control, and this is the response time. Okay. Now we are going for the same using valley constant on time, that means they are analogous, but modulator structure is different. So now we are using, I am using a red color. Okay, so this is constant on time control. This is analogous to valley current mode control, and I want to compare this with our fixed frequency valley current mode control and see what is the, how is the performance, and we have already plotted. So this looks like valley current mode control, that the constant on time is superior in terms of response, and if you go to the inductor current waveform, so this is the inductor current waveform. Okay. So they are designed to achieve close to the same duty ratio. So this is the response time. Okay, this is a very high duty ratio operation. If you see the duty ratio, they are a very high duty ratio operation, because the duty ratio is around 0.67. Okay. Okay. Next we want to compare with peak 1, for this case peak 1, and we want to use green color here, green color. This is a peak, that means constant off time control, but we cannot use a fixed frequency peak current mode control because it will be simply unstable. Okay. And then last one we will see after this will be hysteresis control. So in this case you feel the this one is also fine, it looks also fine under this condition. So if you go to this modulator and if you see the waveform, so these are the comparative response, and if you go to the voltage waveform, so it will come at a time. So that means you can do all this audio susceptibility, everything that you can verify, that we have discussed. Okay. Now the last part we want to check the current loop stability. Okay. So let us go to the current loop stability. and we want to compare, that means if the current loop, if we are close to 6, let us say we are close to 6 and we are setting a band of, let us say 8 ampere band close to 6. So, first we want to see what will be the stability under peak current mode control, valley current mode control, and we are not applying any transient because we do not want to see any transient here. We just want to run it for okay. So, let us see, we want to see there is no ramp compensation, ramp is 0. So, if you see peak current mode control first, let us run, and we want to see what happened in the peak current mode control. So, this is like our input output voltage, like duty ratio is close to 50%. It is just in the, we are setting the critical duty ratio boundary 0.5. Okay. Yeah. So, if you see the inductor current waveform, you will see there is subharmonic oscillation, because if you go here, our switching period is set to point, it should be 2 microsecond, but it is showing 4 microsecond. That means it is totally unstable. You see, you start from here, and if you take few cycle at the beginning, this is like from this to this is our 2 microsecond. So, it is totally unstable, and slowly this current loop become unstable, and it looks like your switching frequency becomes half. But yes, you can see if you very closely look at this, there is a subharmonic instability. So, this is my 2 microsecond, and if you wait for a long time, then it will look like your, this is a totally unstable behavior. Now, we want to run the same scenario with valley current mode control. Valley current mode control, and we want to use red waveform. So, this is the borderline case where, but even with the borderline, they are much, instability is too much because of the, okay. So, if you go to the current waveform here, the similar kind of stability problem you will also find for valley current mode as well. So, it is also not stable, it is also unstable, because the waveform looks like it is, it is, okay. So, both of them are unstable, and if we want to operate now constant on time, that means valley COT, that we are using green color, let us say valley, this is now using constant on time, and if you run it, so under the same condition we are now running constant on time using green color, okay, and this green color will show the actual the stable current waveform, and that we want to see, because in both peak and valley we got totally unstable behavior. Now, if you go to the green color, this is actual switching frequency, because it is perfectly stable, okay, but here the current ripple has significantly increased because of unstable current loop, and this is also evident from our voltage waveform, it is also evident from voltage waveform, okay. So, this is too much instability. So, constant on time, and if you go to constant off time, you can here peak. So, peak, and you can, if I use a black color, this is the last one to compare, and hysteresis is of course stable, there is no question of instability. Then the last one will show that constant off time is also stable, perfectly stable, there is absolutely no problem, okay. Yeah, so this is showing the constant off time control, okay. So, constant off time control, they are perfectly stable, and if you go to the current waveform, they are stable, but the problem with the peak and valley. So, you need to have put ramp compensation for stability, and that will slow down the transient response, okay, and that we will discuss in the design system, but now. So, we have justified, and you can check the audio susceptibility. The current mode control has a very excellent line regulation. So, there is absolutely no problem, it will reject any supply disturbance. So, now if you want to consider worst case scenario, the pulse width modulation, if you take the ripple current, that means the ripple current, for highest input voltage we know the worst case for a buck converter, and this is the expression that we have discussed. If we use constant on time control, the worst case again with highest input voltage, but the expression of current ripple is different. But under constant off time control, it is insensitive to input voltage operation. That is why constant off time control is used for even for LED driving, or also sometime battery charging, because your ripple current, if you fix more or less the output voltage, then that means your delta IL is independent of input voltage. So, if there is input voltage variation, if the output voltage is more or less fixed, suppose if you are talking about a driving an LED, then if you know this value, then you can create a band. So, that means you can set the, if this is our reference, suppose I need to track some LED current, so then my reference current will be simply I LED plus delta IL by 2. Since delta IL by 2 is known for this particular case, so you can implement very fast average current control here. Okay. So, worst case RMS current, this is consistent with the inductor current, because RMS current expression is nothing but, we know that what is the RMS current expression, it is nothing but I average for any waveform into delta IL square by 12, that we have discussed. So, if the ripple current increases, if the delta I is constant, then RMS current will also increase. Switching frequency, that is one of the major drawback in variable frequency control. So, under fixed frequency it is constant, but in constant on time, you see it will be maximum highest switching frequency will happen at the lowest input voltage. Okay. That means for low duty ratio operation, the switching frequency will be low, so you need to adjust. Okay. But for high low input voltage condition or the high duty ratio, the switching frequency can be very high, and then we have to regulate. For constant off time, if you see the expression, the highest switching frequency happen at highest input voltage. That is why we have to carefully select the off time, and that is why the constant on time is a very preferred choice for for low duty ratio operation. So, for low duty ratio operation for VRM, because your on time itself is very small, you can just fix it. So, worst case ripple for boost converter, pulse width modulation, the current ripple of the boost converter is this, and this is worst when the half of the, it is at the input voltage is equal to the half of the output voltage, that means at 0.5 duty ratio. For constant on time modulation, the ripple current is maximum when the input voltage is highest. Okay. So, switching frequency for the boost converter also can be discussed. Under fixed frequency control, this is constant. Under constant on time control, the switching frequency is maximum when the input voltage is lowest, and under constant off time control, it is maximum at the highest input voltage. That means this is when the D is high and when the D is low. Okay. So, then these are the challenges in variable frequency, and we need to regulate the switching frequency by means of, so it is now possible, because if you implement this monoshot timer, if you implement the monoshot timer in digital domain, then you can use an all digital PLL. Okay, because in the monoshot timer, if it is in digital like a counter, then we can using a time to digital converter, that means just a counter, we can count what is the time period, and that can be fed back to a frequency loop by comparing the reference frequency, and then we can slowly adjust the either on time or off time depending upon which regulator you are using, then you can nearly regulate the switching frequency. And in this case, you need a slower switching frequency loop, frequency regulation loop, so that it will not interfere. And in digital implementation, these are very easy, and that is why the constant on off time control are coming with a digitally assisted, even though they are implemented analog in majority of the commercial product, but for the timer adaptation we can use a digital technique, and then you can solve this variable frequency option, but you can get the benefit of the best of their feature. So, variable frequency we have discussed about fixed frequency and variable frequency control. The one more thing I want to emphasize, in fixed frequency versus variable frequency comparison, switching frequency, ripple parameter, transient performance and stability status, these are the very important factor, and we have discussed in variable frequency this is one of the drawback, but you can of course adapt it. The ripple parameters, if we can adapt the switching frequency, it will be the same as your fixed frequency. The transient performance can be improved, that we have also checked, and the stability of the current loop is also checked. But more interestingly, in the recent in APEC 2021, we have shown that even if you take a peak current mode control in mixed signal, that means in digitally controlled converter, if you simply increase the gain, and here the duty ratio is much lower, here your duty ratio is here output voltage is 5 volt and input is 3.3 volt. So, it is much lower duty ratio, 0.5 less than, and you can see from this on time and off time, right. And if we increase, if it is a PI controller, if we increase slowly the integral gain or proportional gain, and this is a discrete time integral gain, then the current loop will become stable even for low duty ratio operation. And if you further increase, this kind of stability can happen where the duty ratio can saturate, and this is called structurally unstable behavior, which can lead to a severe problem in terms of ripple parameter, RMS current, and it can violate the ripple constant, because this will lead to a large voltage ripple also, and that is not acceptable, and this will increase the conduction loss significantly. But if you go for variable frequency digital control, that means if you in variable frequency there is no structural stability, even for the same earlier case, if you go to higher proportional gain for the same PI controller under constant off time control, which is analogous to peak current mode control, there is no structural instability. So, that means even though there can be a stability problem in the closed loop because of the sampling delay, but this stability is much within the limit, and it is not going to significantly increase the ripple current. So, that means at the end I will say, when you go to digital, and if you are talking about fixed frequency and variable frequency current mode control, the variable frequency by inherently provide the inner loop stability, there is no problem. Under closed loop also, even for low duty ratio, it offer better superior structural stability, and of course it will offer superior performance, because if you increase the gain, then you can speed up the response, whereas the previous case you cannot because of the stability problem. So, you can actually increase the performance using this variable frequency control. So, with this I summarize the peak current mode control stability. We saw it require less than 0.5, in fact it can be even less. For valley current mode it should be greater than 0.5. For constant on off time control, there is, and hysteresis control, there is no problem with the current loop. We have shown some MATLAB case study demonstrated to show their effectiveness, and we also shown some comparative case study, those are also presented in order to show different type of current mode control. So, with this I want to finish it here. Thank you very much.